Hello, everyone, and welcome to the second E-RIHS Academy lecture. This lecture is part of the current topics in Heritage Science series organized by emerging professionals. And today we have with us an expert in optics, holography, interferometry, and optical system development. She is a researcher at the Institute of Electronic Structure and Laser of the Foundation for Research and Technology in Greece. She is the creator of the DSP portable system, digital holographic speckle pattern interferometry. Her name is Vivi Tornari, and in her lecture, she will speak about theory, working principle, and applications of this scientific tool in heritage science. Please remember that you can ask questions. Please submit your questions using the Q&A function at the bottom bar of your Zoom window, and your question will be addressed at the end of the lecture. Thank you very much for joining us today. And Vivi, it's over to you.
Thank you very much for the welcome and the introduction, Antonina. So I will, and everybody that is here, thank you very much. I will upload now and share my screen. So today, we are going to, sorry, I have to put this out. Hide video panel. So today I'm going to speak about holographic interferometry and how can be used as a structural diagnosis tool for getting the data, the impact data, from the subsurface and the surrounding of the object of interest. Why it doesn't go? Sorry for that. So the very important aspect when we speak about structural impact data, it is that we speak about a structure, which means that we speak about a system that consists of different parts and connections. Unless we speak about a solid monolithic structure, the rest of the systems are systems that are composed of different parts. And these different parts, they are getting together to give us a whole. This whole, we can break it down in pieces and we can analyze it, and each piece by piece. But in order to understand how it behaves as a whole, we need to have tools to study the behavior of the whole, because if any interconnection or a part of this whole suffers an impact, suffers a defect, this will be visualized, this will be affecting the rest of the whole. So each part affects the whole. And it is very important to be able to understand the condition of the structure in order to be able to assess the problems that this structure suffers and how we can deal with these problems in terms of conservation. In this context, we speak today about structures that are complex composites, like we see that are canvas paintings, panel paintings, and wall paintings. If you see, we we look at a very complicated creation that consists of many layers, and each of these layers is a composite of different materials, both organic and inorganic. So actually we speak about inhomogeneous layered material whenever we speak about a painting that has as a back canvas or panel, wood panel or wall. They are all composites, complex composites. We have that they have certain very important common characteristics that they deserve the definition of the whole. And these are three-dimensional structures. They interact all the time with the environment. They change according to the environment. They give us displacement in the Z direction. They have a lot of interfaces that they are coherent to one to the other. And these layers, they consist of this mixture of different materials that are, as I said already, both organic and inorganic. So these either immovable or immovable structures, they share, no matter how the technique that they have been made or the aesthetic, they share these common characteristics as a whole. And this is very important to consider it as a whole, since interacts continuously with the environment and ages as well as everything with time. So we think about art objects as wholes that interact all the time with the environment, and they are susceptible to deterioration due to this interaction. And this deterioration causes changes in the shape of the structure. This shape of the structure, it is be understood as a moving that happens in the precious surface, because the precious surface, it is what we want to conserve and preserve and provide as a very important cultural identity to the next generations. So whatever's impact on our precious surface, it is very important to be possible to be monitored. When we speak about deterioration agents and we speak about environment, we understand that we speak for a number of different processes that they take place most of the time simultaneously and affect the equilibrium movements. And of course, this is an impact that goes from the outside to the inside of the material and deteriorates and brings decay to the different parts and the different connections that constructs our whole object. And the importance when we speak about subsurface is to understand how the inside affects the surface, how the invisible, minor, small defects may affect the precious surface. Because through this process of deterioration, what exists inside is being affected. And by being affected, it is affecting the surface. In order to affect the surface, means that has the power to give impulse, transfer energy on the top of the artwork, on its surface. So very small defects may give impact on the surface. This impact causes on the surface a displacement. And this displacement, either it comes from direct impact from the outside, either comes from internal defects that they have been generated from the process of the deterioration, they provoke microscopic movements on the surface. And we can identify, we can detect, first of all, we can trace this impact on the surface through special techniques that they can have the sensitivity to record such small impact on the surface, such small movements on the surface. Because we have to keep in mind that we speak about small microscopic movements which affect the surface, so we can have prior to damage understanding of what is going on inside our object and which are these deterioration agents that impact on our object, and they create the microscopic movement on the surface. That's why I introduce to you the holographic interferometry broad technique, because by using holographic interferometry, we actually take the information directly from the surface of the object, and we take this information by using the laser wavelength. Belongs to the broad category of coherent metrology techniques, which coherent metrology techniques use laser sources. And laser sources, they have some unique properties. Among these is the monochromaticity, which means that we can have a selective wavelength in our emission of our laser. This technique, holographic interferometry, is based on three fundamental, very important interrelated physical wave phenomena. These are coherence, diffraction, and interference. We start from coherence. Coherence means that we have a wavefront that has the same phase with the other wavefronts. This wavefront can propagate in space without any change in this phase if we don't cause it. This wavefront can show the phenomenon of diffraction, which means that can bend around object or can go through tiny holes by bending in these objects or holes or slits and continuing the propagation as a new source. At the point of diffraction, the wavefront becomes as a new source of primary source of wavefront propagation by diffraction. And the interference phenomenon, that it is very primal in this application, and it is that we can make the different waves that we need to create our image. We can make them interference one with the other. The interference phenomenon is just a reformation of the intensity of the radiation of our light. And by superposition of these waves, we can create, depending if these waves meet each other in phase or out of phase, we can create constructive and destructive interference. And all this we can manipulate in order to generate visible fringes. The visible fringes of an interferogram, they are coming to us through the manipulation of this phenomena by having, as a result, a hologram image. Each hologram does not give us visible fringes, so we need more than one hologram to get visible fringes. The so-called interferogram, as the one that you see here, it is a visible image. I make here a declaration that in classical optical holographic interferometry, this interferogram is superimposed also on the image of our object. In digital versions, we just get the phase information, so which we translate later through processing on visible fringes. And what we get is an image of visible fringes. In optical holographic interferometry, this image of visible inters overlaps the image of our artwork. So I continue from, that was a parenthesis, I continue from the creation of our visible fringes. These visible fringes, they have an appearance of black and white, signifying the constructive and destructive interference. Actually, constructive interference, it is happening whenever you see light, and destructive whenever you see dark. I'm not explaining here further that there is not actually a loss of energy. The energy goes to the bright ring. What actually we see in this slide is that we have a system of fringes here that you can see that they have a very nice uniform distribution of intensity. This distribution of intensity, it translate to us the reaction, the behavior of the structure as a whole, how the whole of the structure reacts to the increase of the temperature that we impose in this sample, details you can see in the slide. And as the time passes and we increase the temperature, we see this very nice uniform intensity distribution to change. And by change, we mean that we see that it starts to get disrupted. It is not uniform anymore. It is being discontinuous. In order for us to understand what this discontinuity means, we have to follow the changes in the fringes. Here we see the changes in the fringes as a whole, because our sample is a solid structure, it's an homogeneous gypsum plate. So we see that generates this disruption of fringes along the center of the distribution, and we see that it happens in each fringe individual. And as the time passes, it creates small and different fringe patterns. These fringe patterns we can follow each and every one, any distinct one, because it starts the whole, it starts to deteriorate that much that it is not a whole anymore. This information has nothing to do with this information. here we can emphasize each and every one discontinuity and align coordinates, give coordinates, and extract these coordinates from exact positioning and highlight what is going on in each and every point on this panel. I want to stress your attention in another detail that I didn't say, that there is a known crack. Look that the start of the discontinuity of the disruption in the uniform distribution of intensity starts from the point that we know that there is a crack, and from there it starts the let's say the bigger separation of the discontinuities. This is an example for you to understand what we should expect if we have, let's say, a very fresh and defect-free artwork. But this is not the case in most of the artworks, because most of the artworks are very complicated, complex constructions, which tend to deteriorate with time, with environment. So usually when we come to examine them, we find ourselves in more complicated than these situations. So remember that this is a whole reaction. This is the behavior of the whole of the construction, whereas this discontinuities is the information of the localized problems that emerges due to the impact that we load. Here it is the information about the subsurface defects and how we calibrate, how we classify them. We do reverse engineering, which means that we start with known defects, and we put these known defects into experiment and simulation, and by correlating our results through this interconnection diagram that you see here, where we interconnect the results of simulation and experiment, we can derive a classification table where we can know by rule what type of defect we have in each type of fringe pattern. This is an example that I put here to show you the power of repeatability that this technique having for us. These are 10 interferograms taken every 24 hours. You can see the repeatability in the fringe pattern. And also you can see these very, very tiny small changes in the fringe pattern, which allows us to conclude that this is not a copy-paste, this is a completely different pattern. So also I want to stress here your attention in the fact that although we speak about a detachment, we see the microstructure of the detachment. This microstructure can be of a lot of help for a restorer when it needs to do restoration, when it needs to interact with artwork, because you see very well how it is the microstructuring of this detachment. So from here, we go to the development of the digital holographic speckled pattern interferometry, or DSP in short, in a remote portable instrument that allows us to go out of the laboratory, use it in laboratory as well for studies, but go out of laboratory in any environment, as you can see here, for studying any immovable cultural heritage or any movable cultural heritage that cannot go out from a gallery. The principle is that we need before and after displacement. So we create a displacement in our object, either natural, by allowing the environment to do the job, or by induced some disturbance in the object, usually a very small transient thermal disturbance. Here you see the geometry. It is based in the off-axis transmission holographic interferometry geometry. The software, our software is a phase shifting 5-step algorithm. The development, the portable instrument, the post-processing that gives us the possibility to get the surface deformation and the defect on a 3D deformation map. Here are some examples, and here you see a holographic interferometry example. As I said, the holographic interferometry, it is give us both the image of the surface overlapped with the interference fringes. This is an example of how we see it in the holographic interferometry. By studying the holographic interferogram, we can extract any change in the uniform fringe distribution. This is not a very heavy deteriorated example, and we can extract the information, the location and the size and the exact coordinates of each defect, and actually we can measure it in a whole out of local fringe number software to give us the relative displacement of each defect individual. This information is taken directly from the surface of the object. Here you can see some examples from icons. Icons, they have the same structural characteristics. They are multi-layered inhomogeneous structures, which also can be studied with the same way as canvas paintings, panel paintings, and wall paintings. This is another example from the Lucas icon, and this is another example for Byzantine Museum icon, and how we can process the fringe patterns in order to get the exact information about the internal subsurface defects which can impact the surface. What we see, it is the impact on the surface. This is another example from wall paintings, and you can see that here our system scans all the area. This was done, all the requested from the curator areas that we scan, and this took 5 working days actually to do the whole lot of this wall painting. And here you see the interferograms, and the interferograms overlapped with the image of the wall paintings. I want you to notice here that as we see the interferograms, they might look complicated, but they are not. We have a whole body reaction, so how the structure as a whole reacts to the induced displacement, whereas we see localized many discontinuities, which give us the information about the subsurface defects, and we can study these discontinuities one by one. This is a detail of a very important part of this painting. Here you see a deep crack going all along the panel. The wall painting all along the painting, and several other small discontinuities, and we can further process this information in order to get our phase information, and from there we can have the post-processing tools to give a better visualization of the problems. So, for example, as we can see here, we overlap this part with our result of this 3D deformation map, and this is the result that we get. It is actually the result that we give to the conservation responsible for to the conservator responsible for this work. And another important application that I want to give you is the application for environmental monitoring. Here it is environmental monitoring in our climate chamber. We have this DSP climate chamber workstation in the lab, where we can simulate different environments, and by studying in real time the reaction of our samples, so small movable, small, about 30 centimeters, 30 to 50 centimeters, because this is the dimensions of our workstation. We can study in real time the reactions of the object. And here you can see how this is the blue is the rate of deformation, the rate of displacement, and here is the relative humidity. So the relative humidity change, and you see how the shrinking and the swelling of the sample gives us the information about its reaction to these conditions. And here is in this diagram, you see the relative humidity with the mass, because if you see, we have it on a scale, so we can measure it as well and extract the changes in the mass according to the different relative humidity changes that we induce in the chamber. And you can see how well these physical values follow one the other. And this is another example of this application of studying the environmental impact directly from the reactions of your object of interest. It is this samples of 1 centimeter softwood hardwood and 4.5 centimeter softwood hardwood under the impact of relative humidity, and we see the change in the displacement, that is the blue line, whereas the mass is given in the dark line. So we see that how well these two values are following, and how in detail we can study the reaction of the sample, what's going on while we change the relative humidity. And I insist in the fact that we speak about taking this data directly from the sample, and we can feed this data. We can feed this data into simulation, into computer simulation softwares and other important formulations. So we have a number of advantages when we speak about using the DSP method to evaluate the structural behavior of our object. Some of these advantages are very well known, and this is the fact that we speak about non-destructive, non-contacting, non-invasive, non-interacting with a surface techniques, and we apply a full field working principle, which means that we speak about a very, very big diameter of beams. We can go from tenths of centimeters to 1 meter and more. And we have about, we speak about a method that can give us both qualitative and quantitative data. Qualitative is very important while you are working on field, because before you have time to do any processing and post-processing of the data, you get a direct understanding on the condition, on the structural condition of your surface. The vibration, susceptible to vibration, and actually it is something that you have to take care when you apply your techniques. For example, in galleries that are in the middle of the city, and there is a lot of traffic outside, or if your floor is wooden and etc., there you have to have some special precautions. And a major disadvantage is that we have the signal in form of fringe patterns. This is advantage from the point of view that we have a direct qualitative understanding, and disadvantage from the point of view that when we want to make our data quantitative, we have to analyze it interactively. However, it is in our future aim to better drive our analysis by automatic processing. The range of applications, it is huge. We have used this system to make fraud analysis. We have used the system to make before loan and after loan in exhibition in very important paintings. We have used it to check the transportation impact. We have used it to check the handling, packing, to do environmental impact, to do seasonal control. The very, very common application is to have the documentation, the defect documentation, detailed defect documentation for conservators to use it as a defect topography map, and also to risk index prioritization in certain cases that there were a lot of paintings to be restored. And the conservators needed a prioritization list. So there is the application list is actually still open. I discover applications as time passes and new problems come into question. The applications are extended. Thank you very much for your attention. I hope that it was short and comprehensive.
Thank you very much, Vivi, for this interesting and very rich information lecture. We will come back to the topic of holographic interferometry, and we will address the questions that have come during your lecture. I would like to take the chance to invite you all to the next lecture that will be held exactly in 1 month on November 17th at 3 p.m. Rome time. And the next lecture will be given by our next speaker, expert Zvi Koren, who will be speaking about chromatographic analysis of molluscan purple pigments. So you are all invited to attend the next lecture, and I remind you that you can always check the full program of E-RIHS Academy lecture series, and every lecture will be uploaded on the E-RIHS YouTube channel and on the Hyperion E-RIHS website.